Okay, I will explain momentarily how that is going to work with today's lesson. It's really not that awesome in any way, but it does have kind of a little bit of functionality. What we're talking about today is transition state theory. Yesterday's lesson was on collision theory. You must have your reactant molecules collide in order for a chemical reaction to take place. And they can't just collide any old way. They've got to collide in a particular orientation, and they have to collide with a certain amount of kinetic energy in order to break the bonds. I was looking for some new questions for the test that's coming up next week, and I was looking in, I was looking in a database that comes with the new textbook, and one of the questions, and I'm thinking, I'm not going to ask that. The question goes, in your everyday life, please explain a situation where a certain orientation of, must be correct in order to achieve a particular, process. And depending on how your mind is, it's like, what? No, I'm not going to ask that. So then the answer is, oh, I'm recording this. Anyway, get your minds out of the gutter. Anyway, the answer is a handshake. Oh, are you kidding me? A handshake, and then it goes on an explanation. If you don't shake the hands with the right hand and in the right way, you can't achieve the proper. And I'm like, oh my goodness, you people are absolutely insane. So yeah. Needless to say, I didn't put that question on the test. That's crazy. Anyway, all right. So in order for a successful handshake, you need to, a real handshake, not quotes handshake. But, right, in order for a successful chemical reaction, you need to have the proper orientation and you have to have the proper energy to break the bond. Okay. Oh, now I've wrecked this entire lesson for everyone. I'm being evaluated next week. No, it's 2 weeks. It's a good thing I'm not being evaluated today. Transition state theory describes what happens during that reaction arrow, all right? And I've been kind of leading towards this. Like I said in the past, we teach you reactants, products, like some kind of magical poof, takes place, turns the reactants into products. Now we know that they have to collide, proper orientation, proper energy, but still we need to talk about what takes place in between that reactant and product situation, and that's what today talks about. And when we talk about the transition state, we're talking about that transition between reactant molecules and product molecules. And something has to exist there. You can't just have, you can't just have reactant molecules magically become product. There needs to be some kind of physical entity that exists in between the reactants and products, and we call this thing the transition state. Okay. Yeah, this is good. It's what it does. These are 2 bullets that maybe could have been removed, used to explain what happens after they collide, examines what happens as they change the products. That's what transition state theory does. Okay, now this slide is just, again, a representation, and I know it's been a lot of writing last couple of days, but these are new ideas that we need to express to you. This is kind of a step-by-step what takes place during a chemical reaction in terms of energy So again, we can get into our minds what kind of energy conversions do we have taking place. Sure, I could find some better collision carts. These are 16 better days. That's okay. Now, if I removed this third bullet, that the threshold energy is equal to the activation energy, that slide describes any collision that exists in nature, anywhere, all right? Like I said, if I remove that third bullet, ET equals EA, because that bullet there is what brings a chemical reaction into this slide, right? Because the threshold energy, remember, is that kinetic energy needed to break the bond so a reaction can happen. The activation energy is that potential energy needed to have the bonds break. That's the only reference to chemical bonds in that entire slide. If I take this line out, then that slide essentially covers a lesson that I used to do in the grade 12 university physics that was in the unit on energy and momentum. And it describes what happens in any collision, all right? When you guys get to energy and momentum, you'll talk about collisions in the physics. And I can demonstrate that particular slide, again, with my collision cart, all right? When I have any collision take place, and that could be between two colliding carts. It could be between a comet that's being gravitationally affected by the sun and being flung back around by the sun. That actually counts as a collision, all right? It doesn't actually collide, but the comet is being affected by the forces and its direction changed and manipulated by the forces. In physics, that's what we call a collision. Whenever you have one object impart a force on another object, and that causes that other object's motion to change. That's a collision, all right? It could be as simple as somebody pushing on somebody's shoulder, right? Or a hockey collision, two people running into each other, two cars running into each other, two molecules running into each other. They're all collisions, and they all have the exact same features. Here's my collision cart collision, which is nice and easy, so I can describe to you the common feature of all collisions. All right? There, one happened very quickly, and all of these things that are stated on there takes place in that moment when the collision takes place. I used to teach this collision thing in 3 steps. There was going into the collision, the beginning of the collision as the objects are moving closer together. There's the middle of the collision when the objects are actually moving at the same speed. They're at closest distance and they're moving at the same speed. And then at the end of the collision, I called that, exiting the collision, one object is moving a little faster than the other, and they break away and move away from each other. All collisions have those 3 steps, all right? You might be able to see them here. It goes pretty quickly, but there's the going in, and then there's a brief moment where they're moving at the same speed, and then there's the coming out, all right? That's the same with a chemical reaction. There will be a coming in of particles where they'll start to apply forces on each other. There will be a point where they're moving together where if we have our energy requirement, enough kinetic energy, bonds will be made and broken, and then at the end, they'll fly away from each other, and if the reaction was successful, they'll fly away as product molecules. If the collision was an unsuccessful collision, according to collision theory, then they'll move away from each other unreacted. It'd just be a regular collision like billiard balls. At the beginning of a collision, right when they interact with each other, that's the starting point. One object is applying a force onto the other object. When it comes to atoms and molecules, when their electron clouds begin to interact with each other, they're going to push on each other, repulsive forces, just like this spring. And so at that point, one starts to slow down, and the other one in front starts to speed up. They start to push on each other. Now, at that point, when they start to push on each other, the kinetic energy gets stored as potential energy. In this case, the spring gets squished. There's some storage of energy there. In the case of the chemicals, the orbitals might deform slightly. All right, they might actually start to squish the actual orbitals. They might start to stretch bonds. If this was a molecule bumping into another molecule, that might cause the other bond to stretch and deform. Might cause that bond to stretch out like a spring, okay? These are all energy storing situations. So they come together, they exert a force on each other, and they start to stretch each other's bonds, they start to deform the molecules. If, let's say in this, my first example, let's say that this isn't the case. Let's say it wasn't going fast enough. If we didn't have enough threshold energy, then they would simply deform the bonds a little bit, not successfully break them, and away they'd go away from each other, unsuccessful chemical reaction. In the end, yeah, there'd be a little bit of potential energy stored, not enough, and then the repulsive forces would take over, push them away, an unsuccessful reaction, all right? But if we have that proper, let me just clear my screen because I don't have an eraser. If we do have the right amount for a chemical reaction, the bonds will have been stretched enough to the point where right in the middle, there's going to be this thing that exists. That's the 2 molecules moving together. That is not the reactants and not the products, but some kind of amalgamation of the reactants and products that are in the in-between reacted state. There's lots of energy in this state. Bonds are as stretched as far as they can be stretched. As the reaction continues, new bonds are formed, old bonds are broken, and then the new pieces fly away from each other. Okay? The difference between a failed reaction and a successful reaction, in a failed reaction, you get all your energy back and things take off exactly the way they came together. The speeds are the same as they leave. We get all of our energy back out of it. In a successful reaction, if some of the energy remains stored, let's try to simulate a successful reaction. Let's say this is just simply formation of a precipitate, 2 things sticking together. If some of the energy remains stored, now I have to do what I call a hit and stick, right? Now I can't do that here because I don't have the right equipment, but in a hit and stick situation, they would come together and stay together, okay? If energy remains stored, then things will be moving slower afterwards because energy stays stored in the bond. What kind of reaction do we call it when some of that energy remains in storage and doesn't come back out at the end of the reaction? What kind of reaction is that in terms of energy? Pause for thinking back to the last unit, when energy ends up stored in a chemical reaction. Yep, that's an endothermic situation, because they come together, it goes into storage, but then new bonds are formed and it stays in storage. Things move a little slower, the temperature drops, we have an endothermic situation. We could have the opposite situation. I'll try to simulate it with the carts. In this case, I would need my spring already preloaded, right? As if it's got stored energy within itself, within the bonds of this. It makes contact, and that energy is released upon transitioning to the product side. If more energy is released from the bonds, then the final product molecules will take off with greater kinetic energy, and temperature will rise. And that would be an exothermic situation. Okay? But this is true for all collisions. They'll all have that aspect. The exciting part of a chemical collision is that if it's endothermic, some of that energy remains in storage, and things cool down. And if it's exothermic, some of that stored energy comes out and is released as kinetic energy, and things heat up. You have an exothermic situation. And if you don't have enough energy to cause that breaking of the bonds, then things just bounce off. Same energy, no successful chemical reaction, things just go on the way they were. So, again, my 3 steps of the collision. At the beginning, I have a certain amount of kinetic energy of the reactant particles. In the middle of the collision, potential energy is stored in that collision. It breaks bonds and reforms them. Then, as the reaction comes out, we have kinetic energy returned. Sometimes there's more, exothermic, sometimes there's less, endothermic. All right? All collisions can be explained this way. We're putting a chemical flavor on it by putting the requirement for this threshold energy to break the bonds. Okay. Let's now go back and revisit our potential energy diagrams. We've seen these before. These are exactly the same as the potential energy diagrams that we've seen in the first half of this unit. Well, okay, it's 2/3 of the unit on thermal chemistry. And if I have an exothermic reaction, it looks like this, right? I've got potential energy there. Oh, well, sorry, you guys are writing. I'm just so excited. This is the fun part of the lesson. Okay, not the fun part, but a fun part. So again, as I was saying, these are sketches of graphs that we've already seen. Exothermic, potential energy versus reaction progress. Exothermic means I have to lose some potential energy. So my starting energy is high, my ending energy is low, and I've separated these things by a distance for a purpose. And the purpose is, now we can add a middle part, okay? At this point, we know how to describe that drop right there. What did we call that drop in potential energy, that change in potential energy? What was that value called last chapter? Delta H, the delta H. I was concerned there for a moment during the silence, but somebody broke the silence. Nice job. Exothermic and negative delta H, right? Now, what I want to add to the picture today is what happens between reactants and products. And we've just discussed it. Kinetic energy So I've got potential energy of my reactants. Boom, there it is. After I've got the potential energy of my products. But what happens to the potential energy briefly in that in-between state? What happens to the amount of potential energy in my reactant slash product molecules as they're becoming reactants and products? What happens to that potential energy in the middle of the collision? That's the stored energy, right? Potential energy is stored energy. What happens to that stored energy in the middle of the collision? Yep, Christian? It goes up slightly, right? Because bonds are being stretched and deformed and broken, which means to get from here to here, we actually literally have to get up over a hill. I was rolling balls over hills yesterday. That's why I did that. Because we draw the picture like it's an energy hill. Okay, there you go. Nobody sees the humor in that. The reactant molecules have to actually get up over an energy hill, say, in terms of breaking the bonds in order to successfully get to the product molecules. We've already described this little energy hill, and I'm actually going to change colors here so that we can distinguish between it. From here up to the peak of that energy hill, that's the amount of potential energy needed to overcome in order to get to the product side. What did we call that yesterday? The potential energy needed to be overcome in order for a reactant to become a product. What did we call it? Yep. EA, the activation energy. This is EA. Yesterday we just talked about it as being, the amount of potential energy that needs to be overcome in order to successfully have a collision, right? A successful collision. That is kind of graphically that EA. The sizes of these things can have all kinds of different amounts. I can have a small delta H, I could have it down here, and I could have a really large EA. It might not give a lot of energy off, but it takes a lot of energy to break the bond. You could have a chemical reaction that has a large delta H, but the EA is very tiny. It doesn't take much to get the reactant molecules to go. All right? This activation energy, the size of this EA, is kind of a measure of how much of a kick you need to give a chemical reaction. We're now able to explain why, if I have a hydrogen balloon and I want to combust that hydrogen with oxygen to produce water, which is a highly exothermic reaction and happens very spontaneously, why, when I have the balloon and the oxygen just hanging there, why doesn't it just spontaneously go? And the reason it doesn't go, and it doesn't go until I give it a match, is because the molecules are all over here waiting. They don't have enough energy to get over the hill. You put a match to that balloon, you've given them enough energy to get up over the hill, and then boom, they all get over the reaction hump. So that activation energy explains why for some reactions, even though they're spontaneous and exothermic, and the delta S is spontaneous as well, you sometimes need to put a match to light a fire, all right? Because you've got to give it enough energy to get over the activation energy hump, all right? Okay, let's talk about if it's endothermic. It's just going to be the opposite. I'm going to start down here at low energy. We'll change that to yellow. Low energy. It ends up here at high energy. Energy is being absorbed. We have an energy bump again. This literally is like rolling a ball up a hill, right, to get it to a higher spot. Again, this time now, heading up this way is delta H. And again, I'll use the same color for the activation energy. This time, yeah, you might say, hey, the bump is this one, but no, it's the energy needed to get it over that hill. So in this case, the activation energy is right there. If it doesn't make it over that hill, things are going to take off away just unsuccessfully. All right? So now our energy diagrams have a little more detail. They've got that little energy bump that is needed to overcome in order to have a successful chemical reaction. let's define some of these terms. I'm trying to think if I've missed some terms. I can always come back and add them. Don't draw this. This is just a picture that came out of a textbook, which was illustrated a situation. So again, if I've got 2H2 plus O2 to make 2H2O, it's exothermic, gives me lots of energy, but in a balloon it just sits there until I put a match to it, and then that first little bit of heat that I give it sends the first couple of molecules over the hump, right? The ones near the bottom of the balloon now have enough energy to break the bonds, and when that happens, it's exothermic, and it transfers its energy to the neighboring H2 and O2s, and now the explosion proliferates through the balloon, no assistance needed, because all of the energy given off by the products are now feeding the rest of the reactant molecules over the top, and we have a cataclysmic explosion. It's exciting. Too bad I don't know how to do a demonstration like that. That'd be fun to do right now. You'll see I don't have that equipment. Sorry, it's not happening. All right? And same thing, just to kind of illustrate the reverse. This reaction actually can be made to be reversible, because you'll notice my entropy, I've got here two liquid molecules. They're very simple, becoming chaotic gas molecules. But you need super high temperatures. And you need super high temperatures because you need to be able to get those molecules to run into each other hard enough so that you can turn them back into, H2 and O2. And this will not continue. As soon as those first ones get over the top, they're going to suck up energy, and so that's going to deprive your reactants of energy. You would need to continuously feed energy into this system in order to push those guys over the top of that activation energy hill. Okay? You can define those two things. No extra pictures needed. Oh, that was the other thing that I wanted to label on the top of the hill. And you can actually add that to your two sketches. That was the last thing that I knew. I knew I was forgetting something. It's called the activated complex. And the next slide also has a definition of an activated complex. So you can add that, and then I'll talk about what the activated complex is in a moment. This second bullet for EA, haven't discussed that. The higher the EA, the slower the reaction. That's a true statement. You see a big energy activation hump, then it'll be a slower reaction. And that again has to do with the kinetic energy of the particles, and we will discuss that in a moment. Delta H, the difference in energy between the reactants and the products, that is not earth-shattering. And then, again, labeling the peak, and we don't have symbols for that. It's just the activated complex. And again, on your picture, if you could please label both peaks with the activated complex. And we will define the activated complex once everybody is good to go. And this is what this whole lesson is about. This whole lesson is about this transition state between reactants and products. And this thing, this not reactants and not products thing that exists between them being reactants and products actually has a name. We call it the activated complex. It has a lot of potential energy stored in it because there's bonds being stretched and bent and all kinds of things happening. In terms of electrons in their orbits and forming bonds, there are electrons that are in orbits probably that they shouldn't be in, or they're transitioning between different orbits, and there's a lot of energy involved. Notice in bullet 1, it is an unstable chemical species. Even though we describe it as being the peak on the potential energy curve, it is an actual thing. It's an actual molecule, a funny-looking molecule. Partially broken and formed bonds. The potential energy is the highest. It represents the maximum point. It's only formed if the reactants collide with enough energy to overcome the activation energy barrier, and it is formed what we call during the transition state. Now, in the past, we've had handouts that ask questions. Draw a possible activated complex. You guys do not have enough knowledge about bonds and the way things move in order to draw an activated complex. Heck, I don't have enough information. I might have at one point in time when I was fourth year university and I was right into doing that stuff, but actually no, I never took a lot of chemical kinetics. I was not qualified to draw activated complexes. I don't feel you guys have enough knowledge, but let me give you an example of one, but I'm not going to be asking you, draw a possible activated complex, all right? Now, in this particular PowerPoint, it says, draw a possible activated complex for H2O, or H2 and O2, and no, I don't want to do that. So I'm going to give you a different example, and I do want you to write this down, just so that you can see what I mean by an activated complex. I'm going to use the exact same example that I used yesterday when I talked about proper orientation, because this works very well in describing an activated complex. Yesterday, I described to you a reaction between carbon that has three hydrogens, and I'm drawing the hydrogens off in that direction, all right? Because that's the tetrahedral shape that we're going to learn about for this molecule, all right? A molecule that has carbon with 4 bonds will always have this shape of a tetrahedron, like a tripod, 3 legs and something sticking up. And I've taken that tripod and I've rotated it like 90 degrees. And I indicated to you that if an iodine molecule were to come along and have a reaction with this, that it must collide in this particular orientation, all right? Boom, so we've got to have a collision like that. And in the end, and I'm going to draw the reaction arrow to represent the reaction itself, and then I'm going to draw another arrow that draws what happens in that activated complex. So I'm going to show you what's going on in the middle. But in the end, what happens is the iodine runs into the back end, the bond is broken, the bromine flies off the back end, and we end up with those H's flipping around, and I have my carbon with the H's now on the other side, all right? And now I've got an iodine on this side, and I've got an iodine over here with a lone electron, and then I've got a bromine over here, and it also had its electron kind of removed. So now these two could come together, maybe make an IBR or something. Okay? You don't have to draw this in, but just to kind of guide our eyes, essentially this bond was broken here, and we had a bond formed in that position on the back end. Can everybody kind of see that? In the transition state, what happens is you have, and I'm going to start with my carbon, the carbon, and now the hydrogens have been pushed out of that tripod shape into a triangular flat shape. because they're being pushed from the back end. There's repulsion from the iodine's electrons and pushing those hydrogens flat, which means now these hydrogens are sticking up here. There's one, and there's one out here. I'm trying to make this a little bit three-dimensional, but you need to imagine that that's a flat triangle in space. Because now the iodine is coming along here, and its bond is breaking. I put that now as a dashed bond, and I'll change colors here. We have a bond here that's forming. This bond is breaking, and this bond is forming. And as that's taking place, we also have our bromine hanging out here, and its bond is breaking. Okay? So this in the middle right here is our activated complex. If the iodine molecule strikes that carbon compound with enough energy, it will cause those hydrogens to straighten right out, flip right over the top, and literally push the bromine off and form a new bond with the iodine. Question? I can. So it's like where it's purple, is that where the bond is? We've got formation of a bond to get me there, and breaking of a bond to get that guy out of the way. So they're like partial bonds. That's why I've drawn them like that. If you take a look at the carbon, you'll notice it's got 1, 2, 3, 4 bonds, and then 4, and then 5 bonds. That's not a normal looking carbon. Carbon is in a very high energy state there. So like I was saying, if iodine comes along and is able to push that over the top, successful reaction. What do? We head off to here and we have a chemical reaction. But if the iodine doesn't collide hard enough and it comes and the hydrogens, they feel the stretch, but it doesn't make it over the top, what happens? Wasn't going fast enough, Christian. Pushes it back and we head back to here. Unsuccessful chemical reaction. Okay? Which brings me to this. This is my lesson. You see? That's fun. So if I put it in this high energy state, there we are. If we have an iodine come along here and run into it enough, then we'll have a successful chemical reaction. Oh, now it's going to delay. Are you kidding me? Oh, yeah, that's fine. Successful chemical reaction. The reason I have this, you can imagine this little popper thing of having a transition state. What's the transition state for this little toy here? How would we describe the transition state where it goes from one state to the other as it comes through a real high energy orientation of this little toy? Yep. Is it like when it's completely flipped inside out? Because that's actually a stable state, because it'll exist briefly without going through. That's a stable position. Yep. When it's halfway through the popping procedure, can I say that? When it's halfway through that popping procedure, it's really at a point of no return. It's going to end up at a lower energy state, and it's going to continue all the way through, right? When I flip it back, it's like I'm doing an endothermic, non-spontaneous reaction, because it never goes flipped back on its own. So here I'm putting some energy in, and I have to continuously put energy in. I'm putting it through its transition state to a higher energy, slightly less stable state. Now I've got it ready to do an exothermic reaction. Spontaneously, it goes through the transition state, and it results back into the lower energy state. All right? So this thing has a transition state. It's that flat orientation right in between when it pops through. Okay? Is this endothermic or exothermic? I really am not sure. But it does illustrate that in-between high energy state. Okay? I'm not going to make you reproduce that on a test. Maybe I should. I might do that in the future, but I said to you I'm not going to make you do that, so you don't have to worry about that. And I'm not going to make you predict transition states, but that's a good example of a transition state. All right? Okay. Let's now finish off our analysis of this and do some example problems. One last little piece. How does a catalyst work? And I do want you to sketch this. Actually, you know what? I'll sketch it myself on the notebook page. So just put an EP diagram for a catalyzed reaction, okay? Then write what's in the box right underneath it like a little paragraph, and then I'll switch to the notebook and I'll draw a less complex picture. You don't need all that information here. Well, yeah, you do need the information, but I can do it a lot easier than that. Because the question always arises, why is there bumps in it? I should just delete that picture away and then I'll draw it, but we'll save that for the future. So EP diagram for a catalyzed reaction. The catalyst provides the reaction with an alternative pathway with a lower activation energy. That's exactly why a catalyst does what it does. Like I said, it kind of burrows through the hill. That's what it's doing. It's cheating. It's creating like a new path with a lower hill. The picture I'm going to draw for those who are waiting is going to be classic EP reaction progress, however you've been writing it on those others. And actually, I'm going to have an exothermic with a bigger bump, and then in a different color, an exothermic with a smaller bump. I'm going to get rid of all the wiggly bumps here. I think everybody's already done writing, so let's switch back to the notebook. Let me get a new page here. So this is what we're looking at. So reaction progress. By the way, I like you also to be able to sketch these on tests. So remember, we've got the two different types of graphs. You're going to need to be able to differentiate between the two, and I'm going to show you how they're related here in a moment. So all I want here is like starting here, put a bump on it, have it go down there. All right? And this is EP. And this one here is EA uncat. Huh? We like that? You could put the un closer to the cat, I guess. EA uncat. It's the uncatalyzed activation energy. And now all I'm going to do is put a smaller bump here. It ends in the same spot. And this little amount here from my starting point up to there, that is EA cat. All right? That's all you have to know about a catalyzed situation. It simply lowers the activation energy. If you want to apply that to your enzyme biology, blah, 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 right? It holds it in an orientation such that it either makes the bonds weaker, so less of a collision is needed, or it holds it in a good orientation so that you've got more collisions resulting in successful reactions. It simply lowers the energy needed. All right. I do need to do one more comparison before we do some examples. Comparing the EK to the EP diagrams. Don't draw these yet, just put the title. Actually, don't draw those at all because I'm going to make a little switch to one of them. I just want to now put together what we talked about yesterday with the potential energy diagram we just looked at today. Don't draw these because I'm going to do a reorientation, but I just want to remind you, yesterday's graph, number of collisions, or sometimes it's called number of particles. Number of particles or collisions versus kinetic energy. Remember, that was the curve that was like this, had a big bump in it, and then it kind of asymptotically went off like that, right? And if it was hotter, right, it shifted everything over and dipped it down and went off like that. Remember that graph yesterday? Okay. Today's graphs look like this. We have a potential energy. There's a bump. and then it results in a different potential energy. Sound good? What I want to do now is relate this energy to this energy. So the picture that I want you to draw is going to have this collision diagram kind of flipped on its head so we can compare potential energy to kinetic energy. So this is what it's going to look like. So I've taken the collision energy and flipped it, and I have it starting right here at a certain energy because that's going to be my, actually no, it doesn't matter, my starting point can be there. In actual fact, these don't have to be displaced. If you do displace them, don't worry about it. It's really just a graphical representation of what's taking place. So I've taken the kinetic energy guy and I've flipped him around sideways. And I'm going to just put a certain curve on this guy to represent a certain temperature. So it's going to go up, and then it's going to take off like that asymptotically. Actually, it doesn't have an inflection there. It should actually go straight up, but I'm not too worried about that on yours. It actually usually goes straight up like that. And then this guy, I'm going to give it some EA, and I'm going to have him come down here. That's pretty good. That'll work. That'll work for you. And right here is that EA. Any particle going fast enough that has enough EA to get over there will react. Now, if I extend a line from here to there, now that's going to be tough, but you can do it on yours. I can see it right here, right? You're going to go right across to there, right? What's going to be true about of all those particles up there? It's going to be true, Sarah. They successfully made it over the hill. They completed the reaction. If their orientation is correct, they will successfully react because all of the particles up here, right, they have enough EK to react. Successful reaction. The EK is greater than that ET, than that threshold energy that is needed. Right? We call this the EA, but on this graph, we call it the ET. It's the same thing, right? Remember, I said to you it's the same thing, just looking at it from a kinetic energy point of view. So they will successfully react. Now, I wish I had more colors, but I am running out. Let's try the blue one. What does the blue look like? Oh, not bad. Now I'm going to add one more thing. What did I just do? What did I do? I added a catalyst. Make sense? Added a catalyst, brought that down. So this here, EA cat. And I'm hoping that you figured that I'm going to run a line across there and now talk about how many can react. So running a line across here. What's now true? Yep. With the catalyst, and there's more, which means the reaction rate's going to increase, right? It's going to react quickly with the catalyst. So this whole thing, right, and now I'm actually going also into that space there, right? I'm also going into there. That whole thing will react with the with the collision. This is, I'm just going to put here with the catalyst. I think you get the idea. It will have a successful collision with the catalyst. This then here technically is ET cat. All right? Well, it's less. It's been brought that way. We have a greater rate of reaction. Okay? And that's without changing the temperature. If we were to change the temperature, this curve would change, and I'd have more of them reacting without the catalyst, and even more of them reacting with the catalyst. Because now there's more energy imparted to the particles. Okay? That's a fun diagram. He said, with a test on the horizon. Okay, and now one example problem. Oh, one example problem, and then I give you the homework. And again, this sheet is something that we've used in the past, and I see there right on the first one, drawn labeled potential energy diagram, propose a structure for the activated complex. Don't worry about those structures for the activated complexes. If you're feeling adventurous and you can draw some Lewis diagrams, you could fiddle around with it, right? You could do some brainstorming. The reason I don't like well, the reason I don't like it on test is because there's no way for me to say that, no, that's not right. You know what I mean? So it doesn't really test you. Did I count wrong? So for these examples, we're essentially just putting some numbers on our little potential energy diagrams. They do not have to be to scale, all right? I don't need a scale diagram for equal distances for equal amounts of energy. But in order to do this, it's easiest to just draw it on the potential energy diagram and then see the relationship. I think if we sat and thought about it long enough, we could come up with an equation that would, calculate the EA and the delta H for the reverse and all this other stuff. But once you put it on the diagram, it becomes easy. There's no need to kind of get messy with a complex equation here. So we've got a reaction. It's got a delta H of positive 134, and it's got an EA of 143. Again, I'm just making up the questions. Sketch an EP diagram for this reaction. So again, EP, right? Reaction progress. Those are the labels of our potential energy diagram. What type of a reaction is it if the delta H is positive 134? Yeah, Kristen? It's endothermic. That just simply means I need to start off low and I need to end off up here. And you'll notice the EA is actually greater than the delta H. So I guess in theory I should make my hill really high. I don't care about the scale. I would still just draw it like this, put a little bump on it there or something, right? Usually it's more of a smoother bump, but I put them too close together. You get the idea. You could draw it out however you'd like. And once you have that information, simply label your data, all right? Actually, I got to be careful. The EA is 143, but because it's endothermic, the EA starts from there. So it's actually only about 10 taller. So I didn't need to make it a big hump, right? It's the other way around where it's that much higher than the step. So my EA, if I label this up correctly, EA, that length of line is 143 kilojoules. And my delta H here is, again, 134 kilojoules. All right? Label the EA and the delta H. I've done that. I've put the numbers in. Draw a curve that would represent a catalyzed reaction. Ooh, what do I have to do with that? Yeah. Just put a lower bump, right? Good description. Catalyzed reaction right there. You could maybe, if you're answering this on a test, you could put the line here. If you have different colors, give me a little legend there. Or if you don't, you could use a dashed mark, right? A dashed line with your pencil. This reaction can be reversed. Find the EA and the delta H of the reverse. D. Well, let's do delta H first. Delta H reverse. What's the delta H for the reverse? Yep. You bet. It's just the opposite sign. And that's always the case, right? When you flip a reaction around, remember, we change the sign. It's like multiplying it by -1 when we did Hess's law. So that's simply negative 134 kilojoules. Now the EA reverse, we've got to do a little bit of math here, a very little bit of math. I could ask the question, where is the EA for the reverse? But it's easier for me to just point it out. Starting here, the EA for reverse is that little piece right there. So if you draw it up, you should be able to mathematically look at our numbers, look at the relationships. Don't give me a formula, but somebody just tell me, what do I have to do mathematically to find out the length of that if I know the length of this and I know the length of that? Yep. Yeah, 143 minus 134 in this case. 143 minus 134. And what is that? That's 11? 9? 9. Don't ask me to do simple math. It's like spelling. Anyway, 9 kilojoules. All right. The reason I don't want you to kind of memorize an equation is because I could give you an exothermic versus an endothermic, and then you've got the little one here and the longer one there, and you'd have to add to get the reverse. So just draw it on the picture and look at the relationships of the numbers. Okay? And that's that. That is the end of my discussion on transition state theory. Yes?
On the test, are we going to find one delta H or
You mean, do you have to go back and use that other equation that you used in the past? No. No. But that would be fun. I never even considered such a thing. No, I'm not making you do that. But on an exam, that would be fun. Because I have to bring everything together on an exam. And that's just fun. But no, I won't make you do that. I'll give it to you. Okay.